In today's lesson, we're going to extend our conversation about the conservation of energy to specifically talk about the conservation of mechanical energy. So we need to discuss what it is, how you calculate it, and do some problems. So let's go ahead and get started. So types of mechanical energy, what makes up mechanical energy? It's not a brand new type of energy, it's a collection of types of energy that you already know about. And so mechanical energy is basically energy types that can only be affected by pushing on an object with a force. In other words, you can only give it more or less energy when you push on it. And so that includes mainly three types, which is kinetic energy. You can only make something move faster or slower if you push on it to make it speed up or slow down. Gravitational potential energy, you can only make something gain or lose gravitational potential energy if you change its height, which can only be done by pushing on it with a force to raise it, or, for example, with gravity in order to lower it. And then elastic potential energy can only be changed by pushing or pulling on a stretchable object in order to make it stretch. And so we can take a look at the formula for this. The mechanical energy could be the kinetic energy plus the gravitational potential energy plus the elastic potential energy. Based on some of the animations we have today, we can also write it slightly differently and just say mechanical energy is the kinetic energy plus the potential energy. So if we take a look at the different types of mechanical energy just visually to help you out, in this example, this person's giving the object more gravitational potential energy. He puts a force to raise it up. When it gains height, it gains gravitational energy. Here, you can give something kinetic energy by speeding it up. So he exerts a force on the ground, which puts a force on him, makes him go faster, and therefore gives him more kinetic energy. And then here, we've got an object that is being stretched. So as you put a force to stretch the object and change its length, you would give it more elastic potential energy. Now, sometimes mechanical energy is not conserved. It doesn't mean the energy goes away. It just turns into types of energy that are not mechanical energy. So this usually happens when there's no friction or air resistance. The energy is conserved. It goes back and forth between example kinetic and gravitational, but if you add them up, they add up to be the same total mechanical energy. But it's not conserved when there is friction or air resistance. So if there's friction, usually the friction converts the kinetic energy, the gravitational potential energy, into thermal or sound energy. Think about scraping a chair across the floor. As it slows down, the friction causes the kinetic energy to make the bottom of the chair get warm, makes a lot of noise as you hear it scraping. Air resistance. Air resistance can take kinetic energy out of an object and give it to the energy of the air around it. So you think about a car that's moving. If it passes you, you get that big breeze. Where'd that breeze come from? It was the kinetic energy that was coming away from the car as the air pushed it backwards, and that went into the air, created the breeze. Now, here's some examples where the total mechanical energy is conserved. So the mechanical energy stays the same amount because in these examples we have no friction or air resistance. So right down here we've got this cart. As it goes down, it's going to speed up. When it speeds up, it gains kinetic energy, but as it falls down, it loses height, and so as it loses height, the potential energy goes down. But what you see is as it gains kinetic, it loses potential energy, and the total mechanical energy stays the same the entire time. And in this example, we've got a swinging pendulum, and as this pendulum swings, again, it's just going back and forth between gravitational potential energy and kinetic. It's got the most gravitational potential energy right here at the top when it's got the most height, and then at the very bottom, it has no gravitational potential energy because it's all turned into kinetic. If you notice, at the bottom is when it's moving the fastest. So it goes from gravitational potential energy at the top due to the height to the kinetic energy at the bottom due to the speed. And if we were to add these two together, we would have a similar situation as we did over here where the total mechanical energy stays the same. Now, situations where mechanical energy is not conserved, where the energy is turned into other types. Here we've got a car that's driving down the road, and as we mentioned before, when you do that, it pushes the air out of the way, makes the air move so that kinetic energy goes from the car into the air around it, and that's why you notice a breeze. You notice like the leaves kicking up as a car goes by. That's just one example. Another example where the mechanical energy is not conserved because of friction air resistance. Here we've got friction. Now friction creates noise, but also noticeably creates a lot of heat. So if you were to be dragged Not only would it like tear up your clothes and things like that, but you notice it burns because friction creates a lot of heat, turns your kinetic energy into thermal energy. That's also seen if you've ever been in Boy Scouts or you've just seen something on TV where people are starting a fire. They call this a friction fire, where you create so much friction by rubbing that stick back and forth. The thermal energy created when the kinetic energy is converted into friction is enough to actually light the stick on fire. And then if you've ever seen a car peel out, all that kinetic energy, where does all that noise come from? Why the tires smoke? Because the kinetic energy is being converted by friction into thermal energy and sound energy. We have a couple of other examples where mechanical energy is not being conserved, where the mechanical energy is being converted into other types of non-mechanical energy. You're probably familiar with this scene from Men in Black.
Wanna get down on this?
So there, obviously, the kinetic energy, moving energy from the table is being converted to a lot of sound energy, but the table would also be getting hot underneath due to the heat energy being created as it slides across the floor. And actually, let's talk about this one. When we talk about brakes, if you don't know how a lot of brakes work, these are disc brakes. And so as you press on the pedal, the reason why the brakes cause the wheels to stop is that these brake pads are squeezed against your rotor where the wheel is attached, and that friction causes the wheels to slow down. What you may not know is that that friction causes a lot of heat. I've tested it once after teaching this. I drove home, touched my brakes, wish I hadn't. I burnt my finger because it was a long trip home. I'd made a lot of start and stops. Um, and the last one we wanted to show you is right here. And what we see is some cars going around. Now, these race cars have been braking a lot. They've got specially designed brakes that can take more heat without melting. But just to show you how hot brakes can get when you brake a lot due to the friction. So in those examples, you can actually see the brakes glowing so brightly. You can see them in broad daylight because of all that kinetic energy being converted into thermal energy due to the constant friction there as they brake as they turn around the corners. Now, you should have also seen this example when you were doing your FET exercise with the skate park that you should have turned in by now. As you raise the object up, you gain height, so it gains a lot of gravitational potential energy. As you place them on the skate ramp, the energy goes back and forth between kinetic and gravitational potential as they have a lot of speed and a lot of height. As a matter of fact, you turn that speed graph on. So fast speed, a lot of kinetic; slow speed, very little. And then we also have a lot of height for gravitational, very little height for no gravitational. But you notice that the total energy is staying the same. And then when the mechanical energy is not conserved is when you can, through the use of friction, convert it into other types. So we're going to go ahead and put some friction in here. And then as we have friction, you notice they're not going as high, they're not going as fast because the kinetic and gravitational potential energy is being converted into thermal energy. The skate wheels are getting hotter as they continue to spin and there's friction present. So now it's time to put some numbers into this. What we have here is an example of an object falling. Now we've got no air resistance, so the mechanical energy is going to stay the same. It's going to be conserved. So we've got 400 joules of potential energy based off the height of the object and how massive it is, but it's not moving at the top, so the kinetic energy is 0. And then as it falls, it gains kinetic as it speeds up, but it loses potential as the height decreases. So by the time it gets to the bottom, right when it's about ready to hit the bottom, it's got no more height, so it has no more potential energy. It's all that potential energy has been turned into kinetic energy due to the speed it's gained on its trip down. Another example here. If there's no friction or air resistance, then the mechanical energy again is going to stay the same. So we have a skier. As a skier goes down, he's going to gain kinetic energy with increased speed, but lose potential energy with decreased height. And what you notice is in all of these examples, when you take a look at their kinetic and potential energy here, the total mechanical energy in every example is going to add up to be 50,000 joules. So here they're high up, have no speed. Down here they're moving the fastest, but they have no height. And in between, we have a combination of kinetic and gravitational potential as their speed and height has changed, but it still adds up to be 50,000 joules at every single spot. So again, with the pendulum, we can take a look at some specific numbers. As it falls down, you see the height decreasing and the potential energy decreases. But as it goes up, the height increases, and so goes up the potential energy. But look at the speed right here. It reaches the maximum speed, boom, right there. And that's when it had the most kinetic energy. So just putting some numbers on what we were talking about. Let's go ahead and put this into practice. If we have a pendulum spinning back and forth, as we just saw, what we see is at the very top, if we know that it's got 6 joules of potential energy and it's not moving because you're holding it steady, then it's got 0 kinetic energy. And as you let it go, down here at position 2, the height's decreased down to 4 joules. So what's the kinetic energy got to be? Well, we have to remember the total energy is going to stay the same. So if we had a total of 6 joules before, then what would the kinetic energy be here in order to make it 6 joules? Well, you just take the total of 6 minus the potential energy of 4, and you end up with 2 joules. Over here, at the very bottom, where it's got the most kinetic energy, everything's turned into kinetic energy, so 6 joules. So if all the energy of 6 joules is in kinetic, that leaves 0 for potential. And then up at the very top, when it's gone back up to its original height, it stops, so it has 0 joules of kinetic energy, which leaves all the energy in the form of potential energy. So in all of these cases, since energy was conserved, you have 6 joules of mechanical energy the entire time. If we take a look at another example, we've got an object sitting at the top of a roller coaster, and it is 50 kilograms, and it's sitting 4 meters above the ground. So what we can do is we can use that information to calculate some things. Now it does say it's sitting still. So if it's sitting still, you know it's got no speed. The kinetic energy is 0. Using these numbers, we can go ahead and calculate the gravitational potential energy. We've got the mass, we have the height, so you can go ahead and plug those numbers in. The mass times the acceleration of gravity times the height is the gravitational potential energy. So that's 50 kilograms of mass. 9.8 meters per second squared, remember, is g, the acceleration of gravity, times your height. You get 1,960 joules of gravitational potential energy. So what's the mechanical energy? Well, you just add those up to get the mechanical energy, so there's your number. Now for this next example, we have to remember that you still keep that total mechanical energy. As a matter of fact, at each location here, and here, and here, we're going to keep the total mechanical energy because there's no friction or air resistance in this example. So for this one, we've got 3 meters. We can go ahead and plug that into the potential energy equation again. And what we get when we plug in 3 meters is 1,470 joules. So bam, there you go. So how are we supposed to find the kinetic energy? Well, we know that the mechanical energy is the potential plus the kinetic. We know the total mechanical. We know the kinetic. We know the gravitational potential. What we need to do is find the kinetic energy. So when you move this over here, if you just subtract, what you're going to get is 490 joules of kinetic energy. So this is a combination of your old equations and this really simple one where you add them together to get the total. In this example down here, the object's against the ground, so it's got no height, so that means it's got 0 gravitational potential energy. So all the energy has to be kinetic. So all the energy that's left has to be in the form of kinetic energy. So logically, we can just figure that one out. And for this one, we know the speed. The speed is 6 meters per second. And so you can use the speed to find the kinetic energy. Plug that into your equation here. 1/2 the mass times the speed squared. So you plug those numbers in, and what you end up with is 900 joules of kinetic energy. So you plug that in for the kinetic energy. So remember, potential and kinetic have to add up to be the mechanical energy. So if we just subtract these two, we're going to get what you should have for the potential energy, and that comes out to be 1,060 joules of gravitational potential energy. So to sum up, Here are all your energy equations that we've really dealt with so far. We've got the kinetic energy equation and then rearranged for speed and mass. We have the gravitational potential energy equation rearranged for height and rearranged for mass. And then our new equation today, the mechanical energy, is the kinetic plus the gravitational plus the elastic potential, although we really didn't do any examples with elastic potential. So you can really just think about it as the total mechanical energy is usually the kinetic plus the gravitational for the examples we're doing. So for your homework, you should in Canvas have in the quizzes section some questions titled Conservation of Mechanical Energy Problems. Go ahead and do those. When you do those, you should make sure that you reach the minimum score of 80% as it says. If you don't get that, make sure you do them over again until you reach that. If you have questions, please contact me. I will email you back or give you a phone call if you include your phone number, and we'll work our way through it to make sure that you understand what's going on. Good luck.